All right. Let us begin. All right. So let's look at this interim, and I'm going to be very specific to what I think might be on the interim. Which of these forms of carbon can be used as a molecular delivery system? Well, it has to be molecular in size, which means it has to be very small, and it has to be hollow inside. This is diamonds. This is diamonds. This is graphite. These are called fullerenes or buckyballs. This is a carbon nanotube, and this is coal. The only ones that are hollow are the buckyballs, the fullerenes, and the carbon nanotube. So, fullerenes, nanotube. Those are the only ones that are hollow. Only ones that make sense. Which of the forms of carbon could be used to drill into something that is very hard? That would be A and C. A and C. That would be D, E, F, and H. D, E, F, and H, comma, comma, comma. Which of the forms of carbon could be used for pencil lead and why? That would be B, and it's graphite. Sheets, slide. So sheets slide in graphite, which is exactly what you want them to do. Is it recording? Yeah, we're recording. Okay. Woo, I was worried there. Okay, so yeah. All right. Type of bond. Non-polar covalent. Sharing equally. Sharing electrons equally. It's not going to be neat writing. And the most common examples are N2O2, F2, Cl2, Br2, I2, and H2. All the diatomics, that's what they look like. This is ionic because there's been a complete transfer of an electron. I can see that this thing is charged -1, this thing is charged +1, so an electron has been transferred. Electron transfer. Common examples are salt, any salt. NaCl, sodium chloride is the most common one, table salt. Last one is polar covalent. I'm just going to put PC. Sharing electrons unequally. Someone's winning that tug of war, and my carbon monoxide. Let's just say carbon monoxide. That's the first example, but really any two nonmetals that you pick are probably going to be polar, unless you pick something that is diatomic. Okay. So now we move to this model over here. And basically they want us to place the model with the thing. Br2A, that is nonpolar covalent. PCl, nonmetal, B, polar. Because they're two different elements and they're both nonmetals, so we're going to say it's polar covalent because usually only diatomics are nonpolar. Kf, well, potassium's a metal, so I'm looking for a complete transfer of an electron, so I'm looking for model C. Na and O, exactly the same thing. Sodium oxide, transfer of electrons, so that's model C. Carbon monoxide, the classic example of B, nonpolar covalent, and H2, which is a diatomic. Nobody's winning that tug of war. Sharing equally, all of those things are true. So ABC, CBA. How poetic. An unknown substance has a low melting point, is blue in color, and will dissolve in oil and gasoline. Which of the models above represent? Well, like dissolves like. And oil is nonpolar covalent. So the only thing that dissolves in nonpolar covalence is nonpolar covalence. So I'm choosing model A because it is NPC and like dissolves like. Remember what I mean when I say like dissolves like. It means that water will dissolve polar stuff and ionic stuff because it's very similar to polar stuff and ionic stuff. It is polar. Oil will dissolve nonpolar stuff because it is nonpolar and like dissolves like. All right. Sulfur and oxygen, that is covalent. Chemical name is sulfur. Sulfur. Two nonmetals, covalent naming convention. Your thought process should always be, is it two nonmetals or is it a metal and a nonmetal? If it's two nonmetals, it's all prefixes, unless the first atom only has one, and then it's no monosulfur. It's just sulfur, di, 2, oxide. Remember, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms. So sulfur dioxide. Everything else gets a prefix. Pb, that's lead. So lead. I also know that lead has multiple oxidation states, even though it's in the representative elements. Tin, lead, and bismuth. Tin, lead, and bismuth. These three right here have multiple oxidation states, and these three right here do not. They have one oxidation state, and it's on the back of the periodic table. So I'm going to need a Roman numeral here with lead, Roman numeral, which means I need to uncrisscross to figure out what it is. Well, oxygen is charged -2. So if this was -2 and this was +2, then that would be gone from both sides. But because this is 2, I know a 2 has been factored out. So what I know is 2 times 2 is 4, and 2 times 1 is 2. So this is lead 4 oxide. IDE endings for elements. If you have an element in the ending, it is an IDE ending. Nitrous, dinitrogen, monoxide, right? All right, that is ionic. Ammonium permanganate. Well, ammonium's on the back of the periodic table. Ammonium's right here, NH4, and it's +1. So I'm going to write that down. NH4, and it's +1. And then I have permanganate, also on the back of the periodic table because it doesn't end in IDE. Permanganate is an MnO4, and it is -1. MnO4, and it is -1. So crisscrossing done, and that is ionic. And anytime you turn the periodic table over, you should read the top where it says common ion. Ions mean that it is an ionic compound. Nitrogen and oxygen, right up here, both nonmetals. Therefore, I say covalent, and it is dinitrogen, because there are 2 nitrogens, and monoxide. Dinitrogen monoxide. SNO2, that is tin. And I know that tin, lead, and bismuth all have multiple oxidation states, so I know this is going to have a Roman numeral in it. And I know that that is oxide. And this is -2. And if there's no 2 here, then that must be tin-4 oxide. Just like my lead-4 oxide. If you see a 2 here, don't assume that tin is +2, or don't assume that lead is +2. Check the other thing. Make sure that it's not -2 and that you haven't factored a 2 out. Does that make sense? So whenever I see SNO2, I don't want to just go, oh, well, I know what tin is. It's +2. It's not. It's actually 4. This is, if I was making this +4, -2, 4, 2, but then I need to factor a 2 out, right? SNO2. And that's what they gave me. So it is tin-4. It is ionic. Mercury 1 oxide. It is ionic. Mercury is a metal. I know what it's charged. Hg. It is charged +1. Oxygen. Right here on the periodic table, group 16, charge -2. Remember, -3, -2, -1. Nothing. +3. Got all our oxidation numbers on there now, ready to go. All right, HgO is -2, crisscross, and I get Hg2O, and that is my formula. Am I? God, I'm off the. I need to pull this down here to where I can. Okay. There. Now I won't be missing off the page. Hg2O, ionic, +1, -2, crisscross, Hg2O. All right, FePO4, that is ionic. Now I'm going to name this. Is this a transition metal? Yes, it is. Iron is right here. It is in the middle of the periodic table. Therefore, I'm going to need iron, a Roman numeral, and whatever a PO4 group is. Remember, if you have more than 2 elements, it's not an element-ide anymore. It's a whatever that polyatomic ion is called. And in this case, a PO4 group is called a phosphate. It is right here. Phosphate PO4, charge -3. PO4. So I have FePO4. It is charged -3, but I don't see a 3 on the iron. Therefore, this must be +3, and it must have just disappeared off of there. So I need iron 3. PO4 is a phosphate. Phosphate. And then the last one, I have a covalent because it is 2 nonmetals. It is a nitrogen. It is a nitrogen and an oxygen. So therefore, it is a dinitrogen tetroxide. Tetroxide. Remember, we don't put A's and O's next to each other, or O's and O's. So we don't say monooxide, we say monoxide, or we don't say tetraoxide, we say tetroxide. All right, page 1 in the books. Page 2 coming at us hot. All right. Chemical formula, beryllium chloride. Well, beryllium is right here. It is definitely a metal, so it is ionic. Formula, Be, and it has a definite oxidation state of +2 because it is in the representative elements. It is in the alkali metals. +2, and Cl is -1, and if I crisscross, I get BeCl2. AlCl3 is ionic. It is aluminum chloride. No Roman numeral because aluminum has a definitive oxidation state of +3. And as long as it's +3, then I know how it works, and so I don't need to use a Roman numeral. Same thing with this one. Potassium, +1, always +1. So ionic. Potassium. What is a ClO3 group? ClO3 group is a chlorate. Potassium chlorate. That would be a potassium chlorate. And then the next one, carbon tetrachloride, too easy, covalent. As soon as I see prefixes, I know that this is carbon, and this is 4 chlorines. And I'll finish the rest of this up later.